Hi everyone. Our project is about neural network architecture and pruning techniques. We have two mentors, Julia and Adam, and three members on the team, Apuva, Bichen, and Diwan. There are three papers we thought relevant and plan to work with during this project. The first one is about the pruning technique called SNP, which prunes the neural network once at initialization, then only trains the resulting sparse network. By using SNP, we can obtain virtually the same accuracy as if we train the entire neural network, but with less time and less computational power. The second paper is about piggyback, which is a method of adapting a single fixed-tip neural network to multiple tests. In order to do so, a binary mask will be learned for each task. Then, by applying this mask to the fixed neural network, we can obtain a subnetwork with equally good performance on the task. And the third paper is about lottery ticket algorithm, which is about creating a supermask by iteratively pruning the trained dense network. With this supermask applied, the resulting sparse network can actually outperform its dense counterpart.
Our chief goal is to study neural network architectures and pruning techniques to create smaller and faster learning networks. To that end, our current objective is to explore whether SNP technique can be used to create task-specific supermasks using a pre-trained model, and if these can later be used to make other pruning or binary mask generation methods like piggyback faster and more efficient. For creation of supermasks using a pre-trained backbone model, we followed the following steps. First, LINEP5CNN architecture was trained using a dataset. Next, using the other dataset, the trained model was pruned at varying degrees of sparsity. Lastly, the performance of the pruned model was tested on the same dataset as was used for pruning. For the first trial, we trained the model on CIFAR10 and pruned and evaluated using MNIST. For the second trial, we trained the model on MNIST and pruned and evaluated using CIFAR10. In both cases, degrees of sparsity were iteratively increased and accuracies were determined. As can be seen from the results, while increased degree of pruning does improve accuracy on the unseen dataset, however, the accuracy isn't significantly better than random.
So our first conclusion is that as our network becomes sparser and sparser, the accuracy gradually improves, but it is still no better than the random guess. We also say in the iterative method described in deconstructing lottery tickets, the supermask on MNIST gives at maximum 40% accuracy on CIFAR10, and we will take it as our reference point. And thirdly, as is common in any dataset's work, the hyperparameter tuning can be helpful, and in particular, we want to tune hyperparameters with respect to the pruning. For example, we can tune the batch size or the target sparsity rather than the model itself. And we should also notice there is a difference between MNIST and CIFAR10 as labels in the MNIST are all digits. They are of the same category. But labels in CIFAR10 are composed of all intrinsically different objects, and there are plants, clothes, etc. So we need to understand this data formatting difference in testing the pruning techniques. As with the next steps, like I just mentioned, we can try the hyperparameter tuning in the pruning stage. And we can also try different pre-processing methods, because currently we standardize the data before the training. And we should also try initializing the weights in a different way, because one-shot pruning is very weight dependent. Additionally, we can prune and train the pre-trained model on a different data set to see if there is an improvement in the prediction accuracy or the training time. And finally, we can use the piggyback for testing rather than the lottery ticket iterative procedure, because piggyback is superior in terms of time simplicity. Thank you for watching our presentation, and we welcome any feedback. Thank you very much.
I'm Andrei Kapustin. The project is Neural Network Architecture and Pruning Techniques. Mentors are Julia Kempe and Artem Vysogorets. We were initially working with SNP algorithm, but it turned out that it was as good as random pruning with the same sparsity. So we decided to change our approach and use these two papers to create a new pruning method. The first of these papers proposes a pruning algorithm that assigns each connection in a network a score, and connections with the lowest scores are pruned. The scores are updated using gradient descent, and the result of the algorithm is a smaller network that is not trained but has the performance close to the performance of the full network after training. The second paper introduces a way to represent the weight matrix as an element-wise product of two matrices, one of which has rank 1 and is an outer product of two vectors R and S. We combined these approaches and created a pruning algorithm that assigns scores to the elements of these vectors R and S and prunes these elements. Pruning elements of R results in removing all connections coming from one of the neurons on the previous layer, and pruning elements of S removes all connections to the neurons on the current layer. Unfortunately, this approach didn't work this way because the resulting network had very low accuracy. However, pruning neurons requires updating of much less parameters than pruning individual connections. I tried pruning only the largest layer of the network by neurons and prune all the other layers by connections, and as a result, I got an algorithm that works faster than the original one and has pretty much the same performance, and this is the main result of the project. The next steps would be to check if this result holds for other network architectures, and maybe there is some room for improvement of the algorithm.
Hi everyone, welcome to our presentation on non-invertible privacy-preserving representation learning for audio, presented by Team Brian McPhee. So our team comprises of Paula, Param, Ruyu, Preena, and myself, Anusha, and our mentor, Professor Brian McPhee. So the goal of our project was to help preserve privacy of audio data that is distributed through embeddings produced by pre-trained models such as OpenL3, while making sure it's able to perform well for a downstream task such as speaker identification, instrument classification, etc. So to recap, this is what we did before the midpoint. We got the MEL spectrograms from audio data. We passed it through the OpenL3 model, and then we obtained the embeddings. And these embeddings were passed to the inversion model that we created using the architecture of OpenL3 to get the reconstructed spectrograms. And what we intend on doing for the second half of the project is to add countermeasures so we can prevent this reconstruction so that privacy is preserved while making sure that these embeddings still help perform well on our downstream tasks such as speaker identification. So this second half of the project addresses these answers to these questions.
So the countermeasure that we tried was quantization. Quantization is the process of mapping infinite continuous range of values into smaller set of discrete finite values. As you can see from the diagram below, the original input is a smooth continuous curve in blue. Once quantization is applied, each value gets mapped to the nearest discrete value. As a result, instead of a smooth continuous curve, the input now looks like a staircase. Quantization can be done with different bit levels. The number of bits determines the range of discrete values or how many staircases the input gets mapped into. For 4-bit quantization, the original input is mapped into 16 discrete values, while for 2-bit quantization, it is mapped into only 4 discrete values. As the number of bits decreases, the representation of our original input becomes worse. We first applied PCA to the embeddings in order to normalize and discorrelate the features. After that, we applied quantization using 5 different bit values to obtain 5 versions of quantized embeddings. Later, we compared the performance of each version on the inversion model and also the downstream classification task.
So until now, we built an inversion model that is the exact mirror image of OpenL3, where we replace the max pooling layers with upsampling. We also wanted to experiment with more inversion models to improve the reconstruction score. So we also tried to add skip connections we basically tried two types of skip connections. One is the ResNet-like skip connection, and the other one is the DenseNet type skip connection. The DenseNet type skip connections seem to be working the best, and that is why in the following slides you will see reconstructions from this inversion model itself. So here's an example from the inversion model that use the DenseNet architecture.
I'd like a green. I'd like a green. I'd like a green. I'd like a green. I'd like a green.
We can clearly see that as the quantization strength increases, the quality of the audio is decreasing. We wanted to evaluate this model, and so what we did initially was simply use the MEL spectrograms and applied the MSE loss on it and tried to plot it for different quantizations. Here is the result. As we can see, as the quantization strength increases from 8-bit to 1-bit, the MSE loss on the test data also increases, which is something that we expect. We also wanted to compare evaluate on the audio itself and not on the spectrograms. So this is the original audio on the left-hand side.
I'd like a green.
And this is the predicted audio on the right-hand side, which is produced using the Griffin-Lim algorithm. So both of these, the MEL spectrogram, since we wanted to make an apple-to-apple comparison, we also took the applied the Griffin-Lim algorithm to the input MEL spectrogram.
I'd like a green.
And we call it the expected audio. Here's the comparison of the results. We see that between the expected versus predicted, the graph is decreasing, and also with the original versus predicted, the graph is decreasing. But the original versus predicted graph is below the expected versus predicted graph, showing us that there is a decrease in quality due to the application of Griffin-Lim algorithm.
Oh, okay. We also perform the downstream task. It is a multi-class classification model, and we want to see whether the countermeasures still preserve the audio features while perception quality are getting worse. The classification problem is to identify 30 speakers based on their audiobook recordings. Our goal is to remain high accuracy score on classification problem, even on heavy countermeasures. The data we use is from LibreSpeech data. It contains the audio recording for 30 different speakers. And we have about 80 audio clips for each speaker, and we select about 140 1-second audio frame for each audio clips. We did that similarly in the test set, and every speaker has about 16 audio clips. The model we select are random forest and multi-layer perceptron. Here's the result of the random forest model. We try 6 different embeddings as a feature of the model. As we can see, the accuracy decreasing at 4-bit start decreasing at 4-bit quantization and getting worse as the bit getting smaller. The result is similar for the multi-layer perception model. The accuracy drops dramatically at 2-bit and 1-bit quantization. And we can see a clear trade-off between the classification accuracy and the heavier countermeasurement. 2-bit and 3-bit quantization seems to be the best option for distribution-sensitive data based on this downstream task.
So in conclusion, inversion is still possible, leading to loss in privacy, which means we must find new ways to prevent it. And the countermeasure that we used, quantization, seems to be an effective way to hinder inversion. And we should choose the countermeasures and downstream tasks carefully for it to be generalizable. And we really had fun working on this project, and we wish to work on different countermeasures like quantization versions, downsampling, noise injection, work using different data, and work on different downstream tasks. And we'd like to thank our professor, Brian McPhee, and the CBS Women in Data Science team for organizing this wonderful event. Thank you.
All right. Hey, everybody. We are the health web app team. And just a reminder of what we've been working on this summer is a web app to connect mental health clients to therapists and support groups. And so, again, our mentor was Alex Simonoff, who's a CDS alum. And our team members are Yada, Loriano, Tico, and myself, Lauren. And just kind of stepping off of how we updated you at the midpoint process, the main aspects of our project is that we wanted to build this web app that is basically a search engine for someone who's looking for mental health resources. And so the first step with that was getting a database of information about therapists. And in order to do that and to get data into a tabular data frame, we web scraped information from Psychology Today using their HTML structure and using two Python packages, Selenium and Beautiful Soup, in conjunction with one another. And then the other piece of this was our Django app development, which is a Python-based web app. And since the midpoint, we've really just been working on kind of the user interface of the app, as well as linking the database that we had with all of our therapists and making all those views visible in Django. And so we were able to do that. And so for our final update here, we wanted to demo you kind of how this is launched, because right now it's with a virtual environment and using Django, and just kind of show you what the platform looks like. So Tico's gonna walk you through that.
Okay, so as Lauren said, so first thing to do is to activate a virtual environment. You do that by ppnv shell. I think my virtual environment was already activated, and then you just run the server. Takes a little bit of time, and this displays the link that you can just grab and just copy and paste. So this is how our homepage looks like. We also have a therapist view that lists all of the therapists that we have in our database. We filled these fields from the upload view, which is you just do .upload and you choose a CSV file and you upload, and this is the CSV file that we got from our scraping results. You can also create your own therapists if you wanna. We thought that as a user, if you had a good therapist in mind, you could just edit. So there's a way to do that. You just fill in all the fields and then it gets added to our database. You can view the therapist to see more details. You can update it or delete it. Update and delete requires admin login, so not every user can do it, to make sure nobody just deletes our information. So first thing you can do is try to search for the therapist based on what you're looking for. For example, you might be looking for a therapist in Chicago. You just type that into the search bar and you can see all the therapists from Chicago. You can click view to see more detail. You can also look for what you're looking for. Maybe you want to find a therapist who deals with anxiety. All the therapists that show up for New York and so on. So this is the search bar if you want to look for specific therapists, if you do not want to just look through all of the therapists that we have. So this is pretty much what we have accomplished. I think Lauren is going to talk about the next future work, which is expanding one of it is expanding the search functionality. As you see, we try to do multi-search as well instead of just typing individual fields. This doesn't currently work really well, but the idea was to also be able to search therapists based on multiple fields. Okay, I'm gonna take you back to the presentation, Lauren. Okay.
Yeah, so like Tico said, we're really happy to have like a baseline working version of this. We do think that obviously having a multi-field search tool would make it better. We also are all fairly new to HTML, so I think we used a lot of templates to make our UI, and we like the way that the UI looks, but I think we, with more time and more experience with HTML, we could make a better like front end looking user experience. In addition to using like the multi-field search, right now that top search bar on the top right that you saw, that uses an exact string match. So again, we could make it more robust to things like misspellings or abbreviations or just general word combinations by perhaps implementing something that's more of like a name matching string similarity score rather than just an exact match. And then what we'd like to do in addition to, again, make this more robust is extend the method to other data sources. So I mean, I think anecdotally, you see people posting about mental health resources on other places like Facebook or Twitter. So being able to integrate perhaps like social media data in some aspect, which would be a little tricky because there tends to be a lot of noise in that type of data. But we think that would be an interesting way to, better accumulate data sources that don't just exist on this one place, and people who aren't just like formal like licensed therapists as a source of mental health resources. So that's what we worked on this summer. Yeah, we're happy to share the results with you, and thank you everyone for being a part of this.
Bye. Hi everyone, my name is Gabriela Hurtado, and I worked on the text analysis project mentored by Professor Sperling, together with Lisa Combs and Yutong Chen. Over the past couple of months, we have worked to prepare a code package on RStudio for submission to CRAN, the Comprehensive R Archive Network. The package, called Sophistication, provides tools for analyzing the quality of discourse in political text. The theory behind the package and its practical applications are discussed in this paper, Measuring and Explaining Political Sophistication Through Textual Complexity, by Ken Benoit, Kevin Munger, and Arthur Sperling. Additionally, Sophistication is built on Quantita, which is an R package that is on CRAN, and it's for managing and analyzing text, and it was developed by one of Sophistication's co-authors, Ken Benoit. Over the course of this project, we identified and addressed concerns regarding documentation, version incompatibilities, and package size. While working on developing documentation and vignettes for Sophistication functions and applications, we would sometimes encounter bugs in the code or instructions that needed updating, among other things. Once we identified a problem, we would work together to come up with a possible solution, and then we would open an issue on the Sophistication GitHub repository. You can see the tab up here where it says issues. There you can find some issues that we have currently open, which means we have not fixed them yet. There are also some closed issues, things that we brought up early on and have been resolved. We communicated with Ken Benoit, the co-author of Sophistication, and he's also the owner of this repository. And through the comments on the open GitHub issues, we would agree to either implement or modify our proposed solutions. We successfully improved installation instructions for Sophistication, and we came up with a solution for including data packages that are too large for CRAN in the submission. Most recently, we have been drafting a comprehensive vignette for Sophistication, and we have become very familiar with the Sophistication workflow, which I have outlined here. We've been working on developing not only a clear outline of how to use Sophistication, but also useful examples to help guide users. While coming up with our own examples, we have found that later versions of Quantita, specifically versions 2.0 and later, are not compatible with certain Sophistication functions. And after looking into the Quantita archives, I was able to identify a specific problem, and the issue is currently open on GitHub. Unfortunately, Sophistication is not yet ready for submission to CRAN, and the comprehensive documentation is still lacking, although I've included here some examples of the vignette that we have been working on. However, we do plan to continue developing this vignette and to continue to see the issues that we have opened through, to see them resolved and closed, and hopefully we will be able to see the project submitted to CRAN sometime in the near future. Here is another example of the vignette that we've been working on. This project for myself involved a lot of troubleshooting, and it required me to get very comfortable with RStudio. So I gained a lot of skills in that area. I also learned a lot about how to look for possible solutions in code or for inconsistencies, and how to propose and come up with clean solutions. And that's about it. Thank you very much for watching.
Hi everyone, my name is Xinmeng Li. In this summer incubator project, I work with Tianshu and Elena to find a weakly supervised way to localize lesions in CT images. Identifying and distinguishing the various lesions in CT images is a challenging task even to the human observer. Therefore, there are huge demands on developing computer-aided detection methods to assist radiologists and other physicians in reading and comprehending CT images. We aim to adapt and modify the unsupervised object discovery techniques with weakly supervised fashion to the medical image dataset provided by LessNet authors. The framework for a project is that we first retrieve 10 groups of similar lesions as input, then use the embedding of LessNet as the feature maps to generate proposals. Standout score and confidence score are computed. Finally, we will select the best proposals based on the scores. LessNet extracts semantic labels from the corresponding reports of CT images and construct lesion ontology. The label relations are integrated to build a representative target labels for the image. Therefore, LessNet learns the features of various types of lesions and interprets these features to semantic labels. We retrieved 50 images with the closest semantic labels distance to each query image. The first retrieved image shared the greatest number of common labels with the query image. We sort the 500 groups of retrieved image by the label distance sum and select the top 10 groups as sample. These labels describe the body parts, types, and attributes of the lesion. Therefore, for common lesions, it's easy to retrieve images with both close semantic labels and similar visual appearance. However, for real lesions, the visual characteristics of retrieved images might have large variance. After some experiments, we found that proposals generated with features from deeper layer generally provide better core log for the final results. Thus, we incorporate VGG19 architecture into LessNet to replace the original VGG16 setting to retrieve features from deeper layers. This following table illustrates average core log scores of the top 5 and top 1 proposals generated by different deep features. It's clear that the features extracted from ReLU 5.4 of LessNet using VGG19 architecture can improve the results of top 5 selected proposals from 3.2% to 15.2%. However, so far our output is still not very promising. The main problem with our selected proposal is that they are much larger than the ground truth region. Therefore, instead of the standout score, we decided to use confidence score, which favors smaller boxes to select top 5 proposals. We can see that for the same image, when using confidence score, the proposals is much smaller and more centered around the ground truth region. The other direction to solve this problem is to generate smaller proposals in the first place. During the process of creating proposals using CNN features, we modified the function of calculating a list of thresholds on the local saliency map. To be more specific, we use exponential instead of the linear formula. Furthermore, we conduct research over beta global and beta local, which are the thresholds on global and local saliency map respectively. We can see from the following two graphs that when beta local equals to 0.1 and beta global equals to 2.0, core log and positive boxes percentage for all boxes reach the highest. Based on the setting mentioned before, we get our final results as shown in this table. The average core log is about 37.4% for top 5 proposals and 23.2% for the top 1. The top 5 core log scores generally range from 20% to 54% among different groups. Here are some visualizations for our final results. In the decent outputs for the first row, we can see that at least one of the proposals is highly overlapped with the ground truth region. However, for the image in the second row, none of the proposals could capture the true boxes. We found that almost all of the images with nasty output have relatively small ground truth regions. It seems that our algorithms still a little struggled at detecting smaller regions. We can do more research on how to solve this kind of problem to further improve the model performance in the future. Our future improvement directions include generalize the algorithms to a larger dataset, incorporate methods from different research on deep lesion or similar CT dataset with our current model, extract features from activations of CNN pre-trained on ImageNet, and incorporate or adapt other weakly supervised localization framework. We sincerely thank the assistance of Jane, Hugh, the guidance and support of Elena, and this incredible opportunity provided by Women in Data Science. That's it. Thanks for watching.